Hello everyone, this is Professor Roman. Let us continue the group theory lectures. We are now ready to start chapter 6 of the book, Finitely Generated Groups, and also group templates. Well, first we begin with a rather obvious definition. A group G is finitely generated if it is generated by some finite set. If G has a generating set of size n, then we will say also that G is n-generated. So the cyclic groups, for example, are precisely the one-generated groups. But note that saying that a group G is n-generated does not preclude the fact that G might be generated by a fewer number of generators. So, for example, it's accurate to say that a cyclic group is two-generated, even though it's also one-generated. Now, suppose that a group G is finitely generated. A natural question to ask is, does every infinite generating set for G contain a finite generating set? What we know from the definition is that G does have a finite generating set somewhere, but that does not immediately tell us that if you are given an infinite generating set, some finite subset of that must also generate. But that is the case. This is the theorem, and I have left the proof for you to do if you want to. But I'm interested now in talking about something else called the Burnside Problem. This is a fascinating topic in group theory. So let's start with the following question. What does it take to guarantee that a finitely generated group is actually finite? There must be some conditions that are required, because not all finitely generated groups are finite. For example, the infinite cyclic group is one-generated, but it's not finite. So what conditions would force any finitely generated group to be, in fact, finite? Well, we'll start slowly. We might first say to ourselves, suppose the generators are periodic. Suppose the generators have finite order. Is that enough to guarantee that the group is finite? Well, if we look back in chapter 2, we'll find an example there of two matrices. These belong to GL2 of R, and they have finite order, but their product has infinite order. And so the group generated by these two matrices is finitely generated, but it's not finite. And the two generators are periodic, have finite order, but the group is still not finite. So that gives us a negative answer to our question. It's not strong enough to know that the generators have finite order. Now, if G is abelian, then that's a different story, because then every word, every element of G is a word of this form. These are the generators A1 through AN, and the exponents lie between 0 and the order of AI minus 1. They're less than the order of AI. So there are only a finite number of these words, and therefore there's only a finite number of elements in G. So G is a finite group. But we're more interested in the question as it relates to all groups, not just the abelian groups. So we have to raise the stakes. Suppose instead that a finitely generated group is periodic. So the group is periodic, which means that every element in the group is periodic. Every element has finite order. Is that enough to guarantee that the group has to be finite? This question has quite an interesting history. The question, is a finitely generated periodic group finite, was first posed in 1902 by a man named William Burnside. And so it's now called the general Burnside problem. This problem might seem also relatively simple, but in fact, it's far from simple. It took 62 years to discover that the general Burnside problem has a negative answer. In 1964, Evgeny Golod showed that there are infinite groups that are 3 generated and whose elements all have order p to the k. Now, p is a fixed prime, but k, the value of k depends on the element. So they're not, so the elements don't all have the same order. Their order is of the form p to the k. P is fixed throughout the group, but k is not fixed. It will vary. Well, the negative answer we get from Golod's result still leaves open some other questions, some refinements. For example, Golod's groups have elements of arbitrarily large order. In other words, while the prime p is fixed, the exponents k are unbounded. There are arbitrarily large exponents k, and so there are elements of arbitrarily large order. So that leaves open the question of whether all finitely generated groups of finite exponent have to be finite. So finite exponent means there's a single integer m that annihilates all of the elements of the group. Another way to say that is that the element orders are bounded from above, or that there is a maximum element order. Okay, now, this problem is unsolved. Nobody knows the answer. The problem is now known as simply as the Burnside problem, and it has been the subject of a great deal of research. For example, in 1979, it was shown that if m is an integer greater than 665 and is odd, then there are finitely generated infinite groups of exponent m. So the Burnside problem has a negative answer in those cases. In 1992, it was shown that if m has the form 2k times s, where s is an integer and k is bigger than or equal to 48, then there are also finitely generated infinite groups of exponent m. So again, negative answer in these cases. And so the problem, as you might imagine, while simple to state, you have a finitely generated group and all the element orders are bounded. So there's a finite exponent. There's an integer m that will kill every element. Does that group have to be finite? Still an open question. And that's where we're going to leave the Burnside story and move on to questions that we actually can answer. So here is a simpler question. Is every subgroup of a finitely generated group also finitely generated? it would seem like that would have perhaps a positive answer, an affirmative answer. Every subgroup of a finitely generated group is also finitely generated, but surprisingly it's not true. And I have an example here to show that it's not true, but it's not a very simple example. The mathematics is not deep, but the algebra is a mess. It's quite complex. So I'm just going to give you the basic idea, and then if you want to get into the proof, I will leave that for you to do. So we let fx be the free group on the set capital X consisting of two formal symbols, x and y. That's obviously finitely generated. That's generated by the two elements x and y. Let S be the subgroup generated by this set of words over the alphabet, capital X. Y to the k, x, y to the negative k, where k is a positive integer. We want to show, so this is an infinite generating set, and we want to show that S is not finitely generated. And the way we do that is by contradiction. We assume it is finitely generated, so there's a finite generating set that looks like this. And we'll look at the exponents of y in this set, so u1 through un, and of course then their negatives also appear. And the goal is to show that there must be an element in the subset S, the subgroup S, that is not a product or a word over these elements. So we have to examine the words over these elements. They are products, they're products of powers of these elements, but there's some simplifications that may take place when you try to combine these things as concise expressions as you can here. So there may be some cancellation and condensation. In fact, if you just take the product of two of these, there are three possibilities depending on the relationship between the exponents. And by a simple analysis that involves a lot of high school algebra, really, the rules of exponents, we discover that there is a certain exponent pattern that shows up even when you simplify these. And this is what the pattern looks like here, of exponents of y as you scan through the simplified word. And so that pattern needs to be verified by induction. And then we make the observation that in this pattern, I will go back there again, the first exponent is always just of the form k1, and k1 is one of the exponents in this set U that come from the exponents of the generating set. Well, therefore, all we have to do, since U is a finite set of exponents, because it's a finite generating set, all we have to do is take a positive integer k that's not in U and look at this word, y to the k, x, y to the negative k. This is reduced as far down as it's going to go. Pardon me. So it belongs to the subgroup S, but it doesn't belong to the subgroup generated by our finite generating set. Okay. And so we have a contradiction there. So S is not finitely generated. So that was just a quick quick look at how this proof goes. I would encourage you to read it if you have the book, because it's a good example of some of the, how should one say, complications involved in dealing with free groups. What's going on here is you saw all these long equations and things. Well, part of the problem is free groups are free, and so there's not a lot of algebraic relations among the elements of the group, so you can't simplify as much as you might like to. That's just the nature of free groups. But in any case, we do know from this example that it is false that not all subgroups of a finitely generated group need be finitely generated. Now, excuse me, the example that we just did relies quite heavily on the non-abelian nature of the groups involved. As it so happens, all subgroups of a finitely generated abelian group are finitely generated. And this proof is more pleasant than the previous one, but it's still not as simple as you would perhaps like it to be. So one place to start to kind of warm up is to consider the simplest non-trivial case. This is often a useful thing to do. Suppose that G is simply one generated. In other words, G is cyclic. We like to show that every subgroup H of G is also cyclic. And here's how that goes. Since all of the elements of G are powers of the generator A, we can consider the smallest positive power, say a to the k of A, that lies in the subgroup G, AH. This is an extreme witness. We're applying the extreme witness principle by picking the smallest positive power. I probably should have worded, this is worded incorrectly, it's the smallest positive exponent. The power a to the k, A is just an element of a group, there's no order there, so I need to reword this. It's the smallest positive exponent, my error. Okay. Now, if a to the j is any element of H, we can divide J by this smallest positive exponent to get, this is the division algorithm, remainders between 0 and k minus 1. And so we can write a to the r as a to the j minus qk. This can be rewritten here. A to the j belongs to H, a to the k belongs to H, therefore this expression belongs to H. And now, a to the r belongs to H, but r is strictly less than the smallest positive exponent that puts you in H. So the only way to reconcile is that r has to be 0. That means every element of H is a power of a to the k, because j is a multiple of k, so a to the j will be a to the qk, which is the qth power of a to the k. So H is in fact generated by a to the k, and it is therefore cyclic. Okay, this argument that we just gave for cyclic groups provides the basis step for an induction that will work for n-generated abelian groups. So here's the theorem. Any subgroup of an n-generated abelian group is n-generated. And it may be generated by fewer than n elements, but that's not our concern right now. And in particular, any subgroup of a cyclic group is cyclic. That's what we've just proven. So here's how this works. I would suggest that you perhaps pause if necessary to make sure this argument is well fixed in your mind, because it's an argument that uses the division algorithm, and this kind of argument actually occurs in many places in abstract algebra, and we're going to use it in the upcoming proof in a more general, a more subtle way. So, suppose that G is finitely generated by x1 through xn. In fact, n generated. And suppose that H is a subgroup of G. We will prove that H is n generated by induction on n. And we've already taken care of the case n equals 1. So we'll assume that it is true for groups that are generated by fewer than n elements, and we can assume n is at least 2. So if we dump if the last generator, Gn minus 1, is the group generated by x1 through xn minus 1, then every subgroup of Gn minus 1 will be n minus 1 generated. That's the inductive hypothesis. Now, if we happen to be lucky and the subgroup H is completely contained in Gn minus 1, then the inductive hypothesis applies and H is finitely generated, or in fact n minus 1 generated. So maybe I'll change that to n minus 1. So we can assume then, or we must assume, that H is not contained in Gn minus 1. Well, H intersect Gn minus 1 is a subgroup of Gn minus 1, so it is n minus 1 generated. And so it has this form, generated, say, by H1 through Hn minus 1, where the HI's, the little hi's, belong to capital H. Now, every word, little h in H, every element, little h in H, is a word over this alphabet x1 through xn. That generates the entire group G. Now, since G is abelian, we can gather together and single out the powers of the generator xn, the last generator. So little h can be written as some element, a sub h, times x sub n to the e sub h. E sub h is the exponent, and it will depend on h. An is in the subgroup generated by x1 through xn minus 1, so that's in Gn minus 1. So every element in capital H, the subgroup, can be written in this form where we've explicitly picked out the power of xn that's involved in the element H. For want of a better term, since I'd like to refer to this by some term, I'm going to call this a standard form for H. It's not necessarily unique. I'm not saying anything about that. But this is a standard form, and the exponent e sub h I'll call the xn exponent. Now, we are assuming that H is not contained in Gn minus 1, because if it is, we're essentially done. So it follows there's at least one element little h and big H, with a standard form whose exponent is positive. We know there's one whose exponent is non-zero, otherwise h would be contained in Gn minus 1. And if that exponent is negative, then we can take the inverse of little h, and that will give us a positive exponent. So we know there's at least one little h in the subgroup that has a positive xn exponent. Well, then we can again invoke the extreme witness principle to the set of xn exponents, and that will tell us that there is a word, I should say element of capital H, written in standard form this way, AW xn to the EW, where EW is the smallest positive xn exponent among all the standard forms of all the elements of H. That is analogous to what we did in the cyclic case, but of course it was simpler in that case. Now we take an arbitrary, excuse me, an arbitrary element H in capital H. Here is a standard form for it, and we divide the exponent EH by this special exponent, extreme witness exponent EW, and we use the division algorithm. The algebra now is more complicated than it was in the cyclic case, but essentially what we are trying to do is get a standard form for some element whose xn exponent is between 0 and less than the smallest positive exponent. And that's R again. So we're working towards getting an element that has a standard form whose xn exponent is R. And then we'll be able to conclude that R has to be 0. So this is just a string of algebra. It'll bring us to this point here, AH, AW to the negative Q, W to the Q, XN to the R. And then I'm going to combine some of this. I'm just going to write little a is AH, AQ, AW to the negative Q. That's in Gn minus 1. And so what I have here is that H is equal to A, W to the Q, Xn to the R. See, the whole point was to get Xn to the R out of this. Okay, so when you start with the expression for H, you make this substitution, you'll get an exponent of R, then you have to do some algebra to get rid of the rest of the exponent of Xn. And that's what this was all about. So a standard form, not for H, but for, we have to move this W to the Q to the other side. A standard form for W to the negative QH is A Xn to the R. A belongs to H. I'm sorry, I didn't mean H, I meant Gn minus 1. Okay, it's right here. It's kind of hard to keep track of what belongs where. Okay, so I'll circle that. And I'll circle this. W belongs to H, and A belongs to Gn minus 1. And this element, which is in this element, which is in H, has this standard form. But, as I said before, the Xn exponent R is in this range So it's non-negative, but less than the smallest positive xn exponent, so it has to be 0. And so A, which is w to the negative qh, belongs to the intersection, gn minus 1 intersect h. And so h, if I move the w to the q to the other side, h is a w to the q. That lies in the subgroup generated by the little h's. Toss in w so you pick up w to the q. Well, this subgroup contains capital H, because that's generated by h1 through hn minus 1, but it's also contained in capital H because w belongs to h. Okay. And so we must have equality here, and h is in fact generated by h1 through hn minus 1 and w. And that makes it n generated, and that concludes the proof. So not a very pleasant proof maybe, but at least it works. There is actually one more rather interesting, because it's seemingly contradictory result apropos to our current discussion. If G is finitely generated, then we've seen that a subgroup need not be finitely generated. Of course, if the subgroup H is finite, it's finitely generated. That's nothing to write home about. So the very small subgroups of G are finitely generated, and by very small I mean finite. On the other hand, what's surprising is that the very large subgroups of G are also finitely generated. And by very large, I mean they have finite index. So there's a finite number of cosets of H in G. So I've always found this to be kind of a strange result. The very small, while not every subgroup of a finitely generated group is finitely generated in general, the very small ones and the very large ones are. And the very small ones, not surprising, but the very large ones, maybe that's a little bit surprising. So let's take a look at the proof. If G is a finitely generated group, then any subgroup H of G of finite index is also finitely generated. So the way this works is, let's say G is generated by x1 through xn. Every element of G is a word over this set, the x1 through xn union the inverses. So that gives us the negative exponents. We take this. Also, the coset family is finite because that's what the index means. The index is the number of elements in the coset family. So we can write G mod H as T1H through TMH. We don't know how many cosets there are. Whatever the index is, that's the number of cosets, but we know it's finite. And since one of these cosets is H itself, we can assume that T1 is equal to 1, and we get H from there. H1 is H, in other words. T1H is H. Okay, so the set of coset representatives. Now that's not unique, and as we know, any element of a coset is a representative, but I've singled out by name, by symbol, T1 through Tm. These are coset representatives. This set is called a left transversal for H and G. I don't know where that term came from, but it's a system of distinct representatives from the cosets, one element from each coset. Okay. So G then has two representations. It's the words over this set W, the X's and the X inverses. But G is also the disjoint union. These are pairwise disjoint. These cosets, remember, they form a partition of G. So their disjoint union is G. That you could also write that as TH if you wanted to. This is a set product. So it follows that any element A in G can be written as a product of elements from the generating set, W, and I'm not using exponents here. You just write out, it could be x1, x1, x2, x1, 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 x3, and just writing them all out without using the notational convenience of exponents. Okay. But A can also be written, since it belongs to this disjoint union, as T sub k little h, where T sub k is one of the members of the transversal, it's one of the coset representatives, and little h is in capital H. So what we need to do is try to figure out how we can leverage these two expressions for the element A. Well, the second expression tells us something very important, and that is any element of A can be written as a product of an element of the transversal followed by an element of H. And in particular, that applies to any element of the form WT, where W is a generating element, it's one of the XI's or XI inverses, and T is a member of the transversal. So what this is saying is that there must be, let's call it tau in T and little h in H, for which WT is tau H. We are looking at a formula that allows us to interchange the order of an element in capital W and a transversal element. I want to reorder this, put the T on the other side. It changes, but it changes to another element of the transversal. And W, which was a generator for H, must be replaced, or maybe replaced by some other element of capital H. So this is a sort of a commutivity rule, but we're not saying that the elements are commutative. We're just describing how you change the order. Okay. So in words, this says that when we pass an element of the transversal to the left of an element of the generating set, the transversal element may change to a different transversal element, and the element W in the generating element may change to an arbitrary element, an unknown element of capital H. Now, that's just, we're poking around looking for facts, collecting things. And so now, observe, A is the product of W1 through WK. That's one of the forms that A takes. And we can stick a T1 at the end of that because T1 is equal to 1. And now we can begin to pass T1 to the left. It's got a long way to go, perhaps. But the first pass, T1 goes to the left of WK. And so we have W1 through WK minus 1, tau 1, H1. That is this prescription here. When you pass T to the left of W, you get something like this. Then we'll do it again. So we're going to move T1, tau 1, which is a transversal element, across to the left of WK minus 1. We will get a tau 2, H2, and the H1 is still there. And we have one fewer W. Continuing to do this, eventually we'll get the transversal element all the way to the left. So A will look like tau K, HK through H1. So by pulling T1, which was 1, all the way across the word W1 through WN, or M was it? Oh, K, I guess. Yeah, WK. We come out on the far left with another transversal element, and on the right of that, a product of elements from capital H, the subgroup. Well, here is the point now of this. As the element A ranges over the group G, the factors, the H factors here, are produced by this formula. You interchange a T with a W, pull a T to the left of W. But there are only finitely many T's, because that's those elements of the transversal. Let me go back here. There are only finitely many of these, M of these, and there are only finitely many of the elements of capital W, the little w's we're calling them. So as we apply this formula, there's only a finite number of different versions of this formula. So that means that, we can be a little more specific. T has size M, W has size 2n, so the number of little h's that are produced by this process when we do it for all the elements of G is at most 2nm. We get at most 2nm of these h's. Even though the group is infinite, the number of a's that we have to check is infinite. We're producing this expression by interchanging elements of T with elements of W, and both those sets are finite. So we could make a catalog, for example, of that ahead of time and get at most 2nm different h's, and that's all that would be allowed here for all the elements of G. So this implies then that G is the disjoint union of these cosets of H naught rather than of H. And in particular, since H is a subgroup of G, H is contained in this disjoint union. But H is T1H, and that's disjoint from the other cosets TIH. And we have that disjoint union at the top here. Okay. And so H, T1H here, not only is disjoint from the other cosets, but it's therefore a fortiori disjoint from these smaller cosets. TIH naught is contained in TIH. for all I different from 1. So H is in fact in this first coset T1H naught, which is H naught, which is contained in H. So we have equality here. H is equal to H naught, and H naught is finitely generated, so H is finitely generated. Well, in summary then, for a finitely generated group G, the subgroups at both extremes, on the one hand, the subgroups of finite size, and on the other hand, the subgroups of finite index are also finitely generated. But subgroups of, let's say, intermediate size, there are infinite subgroups with infinite index. They may not necessarily be finitely generated.